Hello, everyone. It's time for the last section. We're going to cover section 5.5 on planar figures. We've already looked at situations where we divided numbers given in different units. Next, we will begin to explore what happens when you multiply units together. And we kind of had a little preview of this in a prior section. For instance, feet times feet, I said were feet squared, just like x times x would be x squared. So the product length unit times length unit, or length unit squared, or square length unit, can be interpreted physically as the area of a surface. For example, 3 square inches, usually written as either 3 square inches or 3 inches squared, means that 3 squares, 1 inch on each side, can be placed precisely on some surface. The squares may have to be cut and rearranged so they match the shape of the surface. For a rectangle, we can divide the area into a grid of 1 unit squares. To count the number of squares, multiply the number of rows times the number of squares in each row. Or more simply, we calculate the area of a rectangle by multiplying its length times its width. Area of a rectangle equals length times width. In example 1, we want to find the area of the given figure. We have a rectangle that's 8 inches by 4 feet 2 inches. Conveniently, we're already given a figure with labels for this problem, so we do not need to create a new figure. We need to find its area. To find the area of a rectangle, we use the formula area equals length times width. Notice, however, that the measurements are given in mixed units. One is in inches, one is in feet and inches. Before continuing, let us take a moment to rewrite all of the lengths in inches. So converting the 4 foot 2 inches into inches, 4 foot 2 inches is 2 inches plus 4 feet. We need to convert the 4 feet part into inches. So we multiply by 12 inches per 1 foot, because feet on the bottom will cancel feet on the top. Inches on the top will leave us in inches. 4 divided by 1 times 12 divided by 1 gives us 48 inches. Plus the 2 inches we already had gives us 50 inches. So the length is 50 inches. The width is 8 inches. We plug those into the formula. 50 inches times 8 inches is 400 square inches. The rectangle has an area of 400 square inches. Tables of conversion factors rarely list conversions for area units. Because the area units used for area are usually built from units of length, we can use these unit conversion factors to perform the conversions we need. So 1 foot is 12 inches. To convert 3.3 square feet to square inches, we can first rewrite the units algebraically as 3.3 feet squared, as shown here. This measurement has 2 factors of feet. Feet squared is feet times feet. So the conversion will need to cancel the unit of feet twice. We would use 12 inches over 1 foot and then 12 inches over 1 foot a second time. Having feet on the bottom twice cancels out feet squared. If we only had one of these conversion factors, if it was only 12 inches over 1 feet twice, we would have the weird unit of feet inches left over on the top, because we only canceled one of the units in feet squared, leaving us with feet. That's why we need feet on the bottom twice. Inches on the top twice is what we have left over, and inches by inches would give us inches squared. That's the square inches that we want. So doing the math, setting it up, we start with 3.3 square feet over 1. We multiply by 12 inches over 1 foot. We multiply by 12 inches over 1 foot a second time. 2 factors of feet on the bottom cancel the square feet from the top. Inches times inches on top leaves us in inches squared like we want. 3.3 divided by 1 times 12 divided by 1 times 12 divided by 1 gives us 475.2 square inches. Area units themselves can also appear in unit conversions, and they frequently do in situations involving unit rates. In those cases, the factors of length squared will cancel each other out directly. Here in example 2, we're told that Colleen wants to spread fertilizer on her vegetable garden, which is in the shape of a rectangle measuring 7 feet by 12 feet. If 1 pound of fertilizer can cover 5 square feet, how many pounds of fertilizer does Colleen need for her garden? Well, understanding the problem, we want to fertilize a rectangle that's 7 feet by 12 feet. We're given a conversion factor, 1 pound of fertilizer to 5 square feet. We want to know how much fertilizer we need. So, first we have to find the area. Area is length times width. That's 7 feet times 12 feet, or 84 square feet. Next, we'll use the unit rate that we were given. 1 pound is to 5 square feet. Put the square feet on the bottom, and that will cancel the square feet on top. 84 times 1 divided by 5 gives us 16.8, and our units we were left with is pounds. So 16.8 pounds of fertilizer would be needed for the garden. And no, you're not crazy. I did skip step 2 of the 4-step problem-solving process here, where we would have devised a plan. But the plan we devised is the plan we carried out. Find the area first, then make the conversion. A polygon is a closed plane, flat figure whose sides are line segments. We looked at the area of one type of polygon, the rectangle, in an earlier lesson. In this lesson, we will look at a few other polygons which should already be familiar to you: the triangle, the parallelogram, and the trapezoid. We spent some time in an earlier lesson looking at other properties of the triangle. Now we'll look at the area of a triangle, which is given by the formula area equals 1/2 base times height. So B is the length of the base of the triangle, and H is the height of the third angle measured perpendicularly from the base. To find the area of this triangle here, we note that the length of the base, B, is 6 feet, and the height of the triangle, H, is 20 feet. Or you might say that the base is 20 feet and the height is 6 feet. I think that makes a lot more sense. But base and height are interchangeable because we're going to multiply them together anyway. So We plug in 6 for base, 20 for height, or 6 for height and 20 for base. It does not matter. Multiply those together to get 120. Multiply that by 1/2 to get 60. Feet times feet gives us square feet. So the area of this triangle is 60 square feet. A parallelogram is a four-sided polygon in which each pair of opposite sides is parallel and of equal length. All rectangles are parallelograms, but not all parallelograms are rectangles. We can see that with the parallelogram shown here. But just like a rectangle, the area of a parallelogram is given by the formula area equals base times height. So B is the length of the base of the parallelogram, and H is the perpendicular distance between the base and its opposite side. You can kind of see why the areas would be the same. If we take this triangle formed by the left part of the parallelogram and the height, and imagine using scissors to cut it off, pick the triangle up and place it over here, you can see that we would be left with a rectangle. That's why the area formula is the same. So to find the area of this parallelogram, we note that the length of the base, 10.3 centimeters, and the height is 6.2 centimeters, and we plug these into the formula. 10.3 centimeters times 6.2 centimeters gives us 63.86 square centimeters. Centimeters times centimeters gives us square centimeters. So the area of this parallelogram is 63.86 square centimeters. A trapezoid is a four-sided polygon with one pair of parallel sides, but not two. One way to think about a trapezoid is a triangle with its top cut off. The area of a trapezoid is given by the formula A equals 1/2 times, in parentheses, B1 plus B2 times H. This could also be interpreted as the average of the bases, add them up, divide by 2, times the height. So for a trapezoid, the area is the average of the bases times the height. Looking at this trapezoid we have here, we note that the two bases are 20.4 millimeters and 14.5 millimeters, not milliliters. That would be liquid volume. And the height well, the height I just magically corrected in the figure. So 4.1 millimeters. That 6.2 centimeters was left over from the trapezoid picture, apparently. And I just took these images straight from the book and I missed that it was wrong. So again, the bases are 20.4 millimeters and 14.5 millimeters. The height is 4.1 millimeters. With that, plugging things into the formula, we add together the two bases of 20.4 millimeters and 14.5 millimeters to give us 34.9 millimeters. We multiply that by 4.1 millimeters, the height, and we get 34.9 times 4.1 times 1/2, so times 0.5 or divided by 2, gives us 71.545 millimeters squared. Millimeters times millimeters is square millimeters. So the area of this trapezoid is 71.545 square millimeters. Again, very sorry for not catching that before I started the slide. As we mentioned earlier, every other measurement of a circle, circumference, radius, and even area, can be calculated just by knowing the radius of the circle. The formula for the area of a circle is A equals pi times r squared, where pi is the circle constant, approximately 3.14159 that we discussed before, and r is the radius. Because we only need one parameter to describe a circle, we can use a convenient two-step strategy to solve any problem involving circles. First, use whatever information is given to find the radius of the circle. Then, use the radius that you have now calculated to find whichever measurement you need for the situation at hand. In example 3, a landscaper wants to put a decorative fence around a circular flower bed. If the flower bed is to cover 500 square feet of ground, how much fencing will the landscaper need? Typically, we draw a picture to illustrate the situation. In this case, our picture will not be very interesting. We're told that the circle will cover 500 square feet, or 500 feet squared in algebraic notation. We can recognize that this is the area of the circle by both the context and by the units in which it is given, square feet. So our picture is just this plain old circle. The fencing will be installed around the circle, so the measurement that we need to find is the circumference. We can calculate the length of the circumference by first finding the radius of the circle, then substituting that into the formula for the circumference. So, carrying out our plan, we know the area and we want to know the radius. So we start with the area formula. Area equals pi times the radius squared. We plug in what we know. We know that the area is 500 square feet. Now we need to start solving for the radius. First, we divide both sides by pi. 500 divided by pi gives us 159.15, and that's still square feet. That's approximately the radius squared. To get the radius, we would take the square root of both sides, and the square root of 159.15 square feet is approximately 12.616 feet. Now that we know the radius, we can find the circumference. The circumference formula is 2 times pi times r. We just found r, so let's plug that in, and 2 times pi times 12.616 gives us approximately 79.267 feet, give or take, depending on the number of digits of pi that you used. You might have used 3.14159, or maybe you used 3.14. That's going to affect the calculation. Looking back at our result, the landscaper will need 79.267 feet of fencing, and will probably need to purchase 80 feet of fencing because that decimal is a little bit ridiculous for this design. Why would they purchase 80 feet and not 79 feet? After all, 0.2 doesn't round up. Well, if you only bought 79 feet of fencing, you wouldn't have enough to get around the whole 79.267 feet. So you always buy up when we're talking about distance measuring and making fences or something like that. Most shapes that you will come across in the world do not nicely fit into the classifications that we have here. Sure, it's nice if we have an exact circle or an exact rectangle or a trapezoid or a parallelogram, but sometimes we get something that looks like this. In these situations, we try to break the shape into the more recognizable pieces. Sometimes we can do this exactly, and other times we'd have to use some approximation. For example, this shape containing both straight and curved parts. We can draw two auxiliary segments in the center of the shape, which cuts it into four pieces. Two squares, 1/4 of a circle, and a triangle. So looking at two squares, a triangle, and a corner of a circle, we can find the areas of each of the four pieces and add them together. The area of the whole thing would be the area of the triangle plus 2 times the area of the square, because we have two of them, plus 1/4 the area of the circle. That would have this or this as a radius. So in example 4, Quincy's house measures 40 feet by 25 feet and sits on a plot of land measuring 100 feet by 65 feet. Quincy wants to purchase fertilizer for her yard and finds that fertilizer is sold by square feet of coverage. What is the area of Quincy's yard? So let's sketch a picture of the situation. We have the house. The house measures 40 by 25, and it's sitting on a plot of land that is 100 by 65. We can't just take the area of the big rectangle, because that would include the space that the house is on. What we can do is find the area of both rectangles and then subtract the smaller area, giving us just the area of the yard. So for the larger rectangle, area equals length times width. That would be 100 feet times 65 feet, which is 6,500 square feet. For the smaller rectangle, area is again length times width, so 40 feet times 25 feet. That gives us 1,000 square feet. So the area of the yard, that is just the portion of the big rectangle, not counting the small rectangle, would be a subtraction problem. 6,500 square feet minus 1,000 square feet gives us 5,500 square feet. So the area of Quincy's yard is 5,500 square feet. So that is the end of new material for this course. Go ahead, finish up the 5.4 homework if you didn't get it done already. Get the 5.5 homework done. Next time I see you, we're going to go over the final bit of homework for 5.4 and 5.5. And that will be the last video in the course.